Hi, I'm Trek, and I'm going to do a series on calculus. This is the very first video in that series. It's covering introductory concepts to the derivative, and let's just jump into it. So, entering into calculus from pre-calculus, presumably, it's important to understand that there's sort of a thematic shift as you enter into calculus. Before calculus, you're primarily concerned with questions of what. You're given a bunch of givens, or some conditions, and you are tasked with finding an answer at the end. For example, Jim is traveling to Mississippi. He travels 35 miles an hour, and the previous day he traveled 1,500 miles, and he started in New York. How long did it take him to get there? That's a very pre-calculus type of question to ask. Calculus, however, is much more interested in how functions change, whether it be as they change over time, or they change over distance, or whatever have you, whatever variables you happen to use. Calculus is interested in how things change. For example, it might be interested in asking whether or not the function approaches a certain value as you get way out there into the graph, or whether or not it approaches a value at all, whether or not it's indeterminate, which means that it can't be determined. Basically, it has too many answers. So, thinking about that, let's talk about this function here I have on screen. This is sine of x. It's a pretty cool function. You know, it loops back around and around and around, right round. But more importantly, it is going to help me illustrate. It's going to help me ask our very first question of calculus, which is our fundamental question of our next half dozen videos or so, which is, what is the rate of change of this function at a given point? Let's say 3 pi over 4. And over here I have just some line segments prepared. So don't think about these too much. In fact, I'd prefer you not read them because they have spoilers. But let's say we're interested in knowing what the rate of change is at 3 pi over 4, which is right around here. And what we mean by rate of change is, what is the slope right at this point? I'm going to color the point in. So right at this point, if it were straight, if this function were straight and it were a straight line, what would its slope be? So we're interested in sort of right here at this point, we're interested in the slope of a line that would be parallel to this curve in a sense. That's the way we could approach it, and it's the way I'm going to approach it going forward. We want to put a line that goes right up against the function, and we want to know what its slope is. And that one's right here. As you can see, I have drawn a line that goes and just barely touches the function and keeps going. And we want to know what the slope of this line is. Likewise, I might have asked about a different point, say pi halves, which is right here, and its line that just barely kisses the function. And let's do one more. And over here, another one. All of these lines have slopes, and they are all functions of x, actually. If you notice, this one has a slope and this one has a slope, and they are different slopes than each other, and they vary only by x. As in, right here we have one value, and right here we have another value, and right here we have a third value. And they are varying by x, which means that if we had a theoretical function which tells us the slope of these lines, it also would be a function of x. Okay, let's jump over to another example. Alright, so how do we find said slopes? Well, we're going to jump back many years to a process that you probably remember pretty well, but never really thought about as deeply as you could have, and that would be rise over run. If you are given a simple linear function like the one I have here, f of x equals 2x plus 1, what is its slope? Well, hopefully most of you would think about the old traditional form of y equals mx plus b, where m is the slope, and that's totally legitimate. This line, y equals 2x plus 1, has a slope of 2. And if you see, And how you might verify this is you might pick a point on the line, and you might subtract it from another point on the line. And sorry, let me rephrase that. You might pick a point on the line, and you might subtract its y value from another point on the line's y value, and divide it by its x value minus another point on the line's x value. Let me show you what I mean here. So let's. I've got a few points here. I've got 3 and f of 3, which is right there, and 0 and f of 0, which is right here. And the way I hopefully you've been trained to do this is you take a line, a vertical one, like this, and then you do the same thing horizontal and connect them, and you take this value, which is 6, I believe, 6. Yes, 6. And this value, 3, and you divide the two. So 6 over 3 is equal to 2. And that is the slope of a function. Likewise, you might have been taught to do it like this, where you actually subtract the points from each other. Like, f of 3, which is 7, minus f of 0, which is 1, over f of 0, which is, minus 3, which is our x-coordinate over here, minus 1, which is our x-coordinate over here. And that comes out to be the same value. This is the rise over run method, and it's totally legitimate, but I'm going to show you why it doesn't work for our calculus sort of situation. So let's jump over to our next example. Alright, new function. We're going to talk about f of x equals x squared. So if I wanted to know the slope at, say, x equals 1 right here, why couldn't I just do the same thing? Pick maybe a point right here, and a point right here, and draw lines and subtract the y points, subtract the y values and subtract the x values and divide them together and get a slope. Well, the problem with the rise over run method is that it's an average. It doesn't tell us, for example, the slope right here from this range right here is different than the slope right here, and they're not symmetric or anything like that. You can't just average them and get the value in the middle. So what we'll have to do is sort of modify our rise over run process to try to figure out what the slope is there. First and foremost, let me talk about what we have over on the left here. This down here is just the parameterization of a line segment, which I'm going to turn on in a moment. Which it's actually already on. This just draws a line from a x1 to an x1 plus h. Does that make sense? Like this is x1 f of x1. This is x plus h f of x plus h. So we have this parameterization that draws this line for me. I'm just going to use this to illustrate what's going on here. So in the past, we would have done something like this. We would have taken a line segment going from one point to another, and we were interested in the slope at, let's say we're interested in the slope of 1, so I'm going to increase this to 2. So we would take a line here, and we do rise over run. We draw, our lines. We get our values and divide it out, and we come up with a slope. That's an average slope. What we need is what's called an instantaneous rate of change. And by rate of change, I mean slope, of course. They're interchangeable phrases. So what we do is we actually decrease the length of this down to an incredibly small amount. And we bring it over our area, which we are interested in 1. And we just keep decreasing our h, which remember it's x1 plus h, or x1 and x1 plus h is the distance between our x values. So we want to keep decreasing h to get us a more and more accurate slope, or rise over run. Let me zoom in so you can see what I'm doing. Oops, didn't mean to do that. So where is our 1? Okay, here's our 1. So we are interested in this point right here. So So we want to keep bringing this closer and closer, bringing our x value up and our h value down. And as we do that, eventually we'll get a line that is parallel to the curve, just like we wanted in our initial challenge, which is what we're going for. This is great. This is what we want. So how do we do that? How do we represent making 2 points closer and closer together and drawing a line segment between them? Well, let's sort of do this algebraically. So the basic method that I established in the previous example for doing rise of a run is we take the larger point, the further up into the right point, which in this case is f of x plus h, and we subtract the y value of the smaller point, which is f of x. And then we take the x value of the further point, which is x plus h, and we subtract the x value of the closer point, which is x. And this right here being our x. We're doing this for any case, so we can do this for anywhere. You can move this up to 2, we can move it to 1.4, that's why we're using just an x. It's an arbitrary value. So the keen-eyed among you would notice instantly that the x plus h minus x cancels down to just h. So let me redraw that. Cross that out. We'll just put f of x plus h minus f of x over h. So this is going to be the slope of our line, our theoretical line that tells us the slope of the curve at that point. So we want h to be tiny, but we can't set it to 0 because that would be the same point. If x, if we have one point at x and another point at x plus h, if h is 0, then they're the same point. And if you remember back to elementary school, you can't create a line that's with only one point. You need at least 2 points. So h can't be 0, and it's undefined as 0. But we want it to be infinitesimally small. We want it to be so small that its difference is, non-existent. In fact, we want it to be like continuous. I can't really explain that just yet, but hold on to that concept, because the next thing we're going to talk about are limits, which is how we're going to approach the idea of bringing h to 0, but not quite there. That's in the next video, so I'll see you there.